дорогие коллеги, которые откликнулись на наше предложение прийти и вот, послушать лекцию профессора Павлоса Лагудакиса. На самом деле, те работы, которые предполагается рассказать на этой лекции, они самые современные, они относятся к передовому краю исследований в области фотоники. И почему я так говорю? Потому что большинство работ Павлоса опубликовано в журналах Nature, PhysRef Letters и других журналах. Делалось это в основном всегда впереди других групп. И тема, которая здесь будет говориться, она озвучена, она про конденсаты, причем конденсаты не атомарные, не те, которые, за что была присуждена Нобелевская премия, а те, которые делаются вот ближе к тому, что изначально было с фотонами, но в данном случае эти частицы живут в твердом теле, и это немножко отличает. Это поляритоны. И чтобы вы знали лектора, я немножко расскажу про биографию Павлоса. Значит, Павлос по национальности грек. Значит, он окончил университет в Афинах в 2000 году. В 2003 году он получил уже через 3 года, ну, как по нашим меркам, так и должно быть, через 3 года получил PhD в области физики от университета Саутгемптона и продолжил свои исследования в области исследования оптоэлектронных свойств органических полупроводников. То есть органические полупроводники – это вот тот материал, который и вот составляет основу того, что будет рассказывать. Он делал это в Германии, в университете Людвига Максимилиана. В 2006 году он возвратился в Саутгемптон в качестве лектора и профессора. Он с 11 по 14 год возглавлял кафедру в университете и был директором департамента физики и астрономии в этом университете. В 2016 году Павла пригласили в Сколтех, где он сейчас руководит лабораторией гибридной фотоники и в то же время является вице-президентом Сколтеха. Сколтех – это не Сколково вообще, это университет исследовательский Сколково по фотонике. И вот его достижения отмечены несколькими премиями. Одна из премий была в 2011 году. Это премия, значит, по квантовой электронике. Он получил ее в Сиднее. А вот последняя премия – это премия, которая была учреждена в России, премия «Вызов» по как раз в номинации «Прорыв». Вот Павлос является первым лауреатом этой национальной премии Российской Федерации. У него, значит, больше, чем там сотни работ, я вам сказал, в каких журналах. Вот. И мы, конечно, очень признательны Павлу, что он вот буквально пригласили, он сразу же согласился, откликнулся. И вот в тех разговорах, которые уже состоялись, высказано вот пожелание, чтобы мы как бы наши усилия, которые у нас есть общие, реализовали в совместных проектах. Для этого тоже, возможно, вот Сергей Васильевич присутствовал, обсуждал это, тоже еще существует пути. Поэтому, Павлос, thank you for coming, and we are going to listen to your lecture. As we discussed, 1 hour and 20 minutes. So, it's yours, please.
Thank you very much for the introduction. That was one of the lengthiest introductions I ever had, although I didn't understand much of it. And thank you very much for the invitation, Professor Kili. I'm honored and humbled to be here, actually, at an institute that has really made contributions to the field of light-matter interactions over decades. Yes. So today I will be talking about some of the work that we have done at Skолтех. Skолтех is a relatively new university in Moscow. As probably you heard during the introduction, I started at Skолтех in 2016, where we were given a first lab in in a temporary building, and there is nothing more permanent than the temporary solution, so we are still there. So we had already designed all the spectroscopic setups for which I will be talking about, and already in 2017, we were very lucky to be able to demonstrate at Skолтех the application of quantum fluids of light for quantum simulation as optical transistors, single photon switches, and also as superfluids. So just to bring you inside the field, I will give a short introduction, which will be from a bird's eye view, and then I will go to greater and greater depth, hoping to bring you all with me. So the system that we are studying is consisting of two mirrors. So we have two mirrors in which we confine the optical field, and within these two mirrors, we are positioning a semiconductor which is resonant with the cavity. And if I play this again, there we go. So the photon creates an electron-hole pair, an exciton, and the exciton emits back into the cavity. And when this exchange of energy is faster than any loss mechanism in the system, then you get into the strong coupling regime, where practically the normal modes of the system are not anymore excitons or photons, but what we call polaritons. So I will be talking today, therefore, about polaritons, a field that bridges the fields of photonics, because we are dealing with partly photons and partly electronic excitations, and how we can apply that for computing applications. And I will have two parts in my talk. Hopefully we can go through both parts. The first part will be on optical computing, so digital computing in full logic using polariton condensates. This is work that we have done with IBM. And the second part will be about analog computing, also called simulators or optimizers. So going a little bit greater into depth about the nanostructures that we use in order to create this kind of Bose Einstein condensates of excitons and photons, we are dealing with cavities that they are consisting of two distributed Bragg reflectors. These are heterostructures with very high. Tell me what you want to this one, yeah? No, the other one. Okay. Person? No. Okay, so let's go on. We have a cavity which is usually it is a λ/2 cavity or a 3 λ/2 cavity. It is a small cavity so that we have small volume, and therefore we can increase the Rabi splitting in the structure. But before I go there, let me show you the reflectivity as a function of wavelength. By using this kind of distributed Bragg reflectors, I create a stop band where I have practically reflectivity of almost 100%. And here you can see the cavity mode, the bare cavity mode. The photons that are coming out of the structure, they can be coming out at normal incidence, but also at an angle. So the photon can have an in-plane momentum inside the cavity. And now what we do, we position a semiconductor resonant to the antinode of the field, and the semiconductor has an optical transition which is resonant to the cavity, and therefore now I will have an interaction strength of mega, which when it exceeds the loss mechanisms in the system, such as the photon decay or the exciton non-radiative recombination channels, then we enter the strong coupling regime. And if I look now at the reflectivity from this structure, instead of just looking at the bare cavity mode, I see two reflectivity minima. Yes, these are like the two solutions of two coupled pendulums. These are the new normal modes of the structure, which we call polaritons. Going yet one step deeper inside, I can therefore describe the polariton as an admixture of a photon and an exciton. There's a little delay between my pointer. Maybe I can use your other pointer. So, and these coefficients that really here simplistically describe the photon and the exciton component, they are the so-called Hopple coefficients. Professor Gravinovich derived exactly the same formulation back in the 60s, a few years later. But practically what we get from the photon part, we have now quasi-particles which have very low effective mass, as you can see here, orders of magnitude smaller than the effective mass of the electron inside the semiconductor. And we also get, due to the photonic part, a short lifetime. Even if we have very high quality factor cavities, the lifetime is approximately 10 to 50 picoseconds. These are several thousands of bouncing of the photon inside the cavity before it leaks outside. From the exciton part, we get very strong nonlinearities. So we have excitonic interactions. Exciton-exciton interaction is what enables, for example, polaritons to thermalize. And of course, the exciton is included in the polariton, and therefore I also have polariton-polariton interaction. Okay, so now if I take, for example, and I diagonalize this matrix, I get to the new solutions of the system, which are trivial here, and they are trivial as long as we are considering the energy of the exciton and the photon as a discrete state. So here, if I bring them in resonance, I will have the upper and the lower polariton mode. But as I said earlier, the photon inside the cavity is not only the photon that I have at zero angle, zero in plane momentum. If I look at the dispersion of the photon in the bare cavity with the green dust line here, it is parabolic. That is because we have confined one direction. So I go from a conical to a parabolic bare photon dispersion. And therefore, now if I couple the photon with the exciton is also a parabola, but because it's much heavier, it appears to be completely flat for the range of angles that I can access experimentally. Now, strong coupling does not occur only at normal incidence, it occurs at every wave vector. And now if I couple this point with that point, I get these two new modes. Therefore, the system has now a new dispersion, which we call the upper and the lower polariton dispersion. And these dispersions, they look and they are very different from the bare modes. Okay, I can play with the resonance between the bare exciton and the bare cavity mode and change the shape of the lower polariton mode. If I go to negative detuning, that is bringing, for example, the cavity mode at a lower energy than the exciton mode, this lower polariton dispersion will become much deeper. So I can really play with the energy momentum relationship of the system, with the effective mass of the system very easily, and I can exploit this as we will see later. So now polaritons have shown that they undergo Bose Einstein condensation. Well, yes, it is a composite particle of two bosons, the photon, which is a clear boson and you understand, but also the exciton, which is a composite boson, and through the photon part, we dilute the exciton. So we can put many more excitons together without reaching the mode transition. And therefore, back in 2006, there was the very first demonstration. Here you can see photoluminescence from the lower polariton dispersion. As you increase the density of polaritons in the system, you see that you go in the reciprocal space to condense into a state which has a macroscopic coherence. So the first demonstration of Bose-Einstein condensation was done at cryogenic temperatures. Actually, with my very first PhD student in 2007, we demonstrated at room temperature in a bulk gallium nitride microcavity polariton lasing. And then in 2013, a group from Würzburg, the group of Sven Hoffli, demonstrated that actually you can use the fact that you are dealing with semiconductor nanostructures and you can inject carriers electrically and create the first.
What is the picture snapshot of the light?
Yes, so the picture here that you see, this picture is what I was showing before, energy versus in-plane momentum. They have not plotted on top the dispersion, but the dispersion is this lower polariton dispersion. And you see the photoluminescence as you increase the excitation density. So here you are below threshold, and you can go above threshold. And once you hit threshold, you see the collapse of all the polaritons in the reciprocal space. They all come out from the normal incidence, yes? So they collapse across the polariton dispersion to the ground state. Can you hear me without the microphone better or with the microphone?
Microphone is better.
Microphone is better, okay. So moving on, in 2009, there was the first demonstration of an indication of superfluidity from polariton condensates, where practically what they were doing, they were injecting polaritons resonantly at the ground polariton state, and they could see that by increasing the density of polaritons, they could really create a superfluid that goes through a defect without creating ripples. Yeah, and this is a property of superfluids, when you really go through a defect without scattering. And that was again repeated in 2017 with room temperature with organic microcurrents. Okay, so this is a brief introduction about polaritons, polariton Bose-Einstein condensates, and now we are going to look into how we can use these quantum fluids of light for optical computing. The very first demonstration of an optical transistor with polariton condensates, how we can really put several of those together to create universal gates. Universal gates, there are two, the NOR and the NAND gate, and they allow you to do full logic. And finally, let's get into it, why one would like to make optical transistors, why one would like to have optical computing. Well, this is something that really comes from the fact that if you look here on this map, and you look with the green squares, you see this is the frequency of the processors as it has been increasing, similar to the Moore's law. This is the so-called Dennard scaling law, where practically in 2005, some of us in here will remember that our computers plateaued in speed. We had computers with one processor, and the speed of the processor was increasing every year. At 2005, from one processor, we stayed at 3 gigahertz, and we went to the so-called dual core. Yes? Then we went to quad core, octa core. My computer now has 96 cores, but the frequency, the clock of the processor is pinned at 3 gigahertz. Why? Because if you go faster, this is an electronic transistor, you generate too much heat, you just burn it. So if you really want now to go above the 3 gigahertz, you need to play with something which does not generate so much heat. This can be photons, and actually, this is the field of optical computing. So you want to use photons, and the main property that you want to have is to be able to switch off a light beam with another light beam. And to do that, you need a nonlinear crystal. Usually, nonlinear crystals require, they have weak nonlinearities, so you need to have bulk crystals, and that immediately kills scalability. Because if you want a centimeter crystal for one transistor, you can forget about putting thousands of them together. So really, if you want to reach this optical computing, you can go down to the quantum limit. Potentially, you can go to single photon operation, so you can switch it on and off with one photon. You can go to terahertz speeds, but of course, you will never be able to reach the densities that we have with our electronic transistors. However, that is not a problem. There are many applications where speed actually matters, and you can really do with less transistors, but much higher speed. Okay, so how are we going now to create this kind of optical transistors with polariton condensates? The system that we use, we inject carriers inside optically, non-resonantly. So we use a laser beam, and we inject an electron hole plasma. So these are electron holes, which relax in energy. This is the in-plane momentum of the cavity we were talking about. You can see here with orange the lower polariton dispersion. And once these excitons relax on very high in-plane momenta outside the light cone. They relax in energy, and eventually they form polaritons. And what you want is to create a high density enough of polaritons so that you reach occupancy of 1 at the ground polariton state, and then through stimulated relaxation, all polaritons will go and form a macroscopic coherent state, the Bose Einstein condensate of polaritons at the ground state. Okay, so how polaritons use energy in organic semiconductor microcavities, in organic polaritons? Well, in general, one of the main processes when we are dealing with excitons is that of the fermionic exchange interaction. However, when you are dealing with organic semiconductors, that's when you go for room temperature, large exciton binding energy, you have localized excitons. Every molecule is populated by one exciton, and therefore exciton-exciton interaction, the fermionic exchange interaction, is quenched. So you have very weak per-polariton interactions. So that is actually a limiting factor which is present in organic semiconductors, but not in bulk inorganic crystalline semiconductors. Now there is another way, that of intracavity pumping. Not all molecules inside the cavity of the semiconductor that you embed between the two mirrors are strongly coupled. Some they are at the antinode of the field, at the maximum of the field, but some molecules lie on the nodes of the field. And therefore, you have material which is not strongly coupled and fluoresces resonantly to the Stokes shift within the lower polariton mode. So due to the large Stokes shift, you can really now within the cavity pump the lower polariton dispersion and increase the density of polaritons at the ground polariton state. There is another method that we actually studied now more than 10 years ago, and we transferred to organic semiconductors by some first studies that we did in my group on inorganic structures. So that is really relying on the so-called vibron-mediated relaxation. Those who have been working here with inorganic semiconductors, you know that we have modes, vibrational modes, the so-called phonons, with which, if you use, for example, an low phonon, you can lose a lot of energy with one particle emission. So we studied back in 2011 how you can actually use, instead of phonons, vibrational modes of the molecules to really release a lot of energy in one particle. And this is actually what we found to be a very, very efficient process. You can really, with one scattering event, emission of one vibron, you can use up to 300 MeV, which is a very large amount of energy for this kind of semiconductors. So then we started a collaboration between Scotech and IBM back in 2016, where practically at IBM, they could design a structure that has a ladder-type polymer inside the cavity. So here you can see the device that IBM made for us. In this device, they had actually first seen polariton Bose-Einstein condensation at room temperature in 2014. And the secret of this device is the following. Being a ladder-type polymer, it has very stiff bones, which means very, very high energy vibronic modes. And when you look at the Raman spectrum and you convert these to vibronic resonances, you see that you have vibronic resonances which carry a lot of energy. 164 MeV with one vibron, or 200 MeV with one vibron. So at that point, I wanted to see if we can apply the studies that we have done in J aggregates and inorganic semiconductors, utilizing phonons to dissipate energy, to do the same thing with this kind of very stiff molecules. And by doing that, what we observed is that actually we can lower the condensation threshold. So here you can see the photoluminescence intensity as a function of the excitation density where you hit threshold. So you have a nonlinearity. That is the point where you form the polariton laser, the ground state polariton condensate. You can see that the energy is increasing. That comes from a quenching of the Rabi splitting. And you have a line with narrowing at threshold, which is characteristic of the formation of coherence. So when we did this, we observed all the characteristics of Bose-Einstein condensation, as IBM had done by pumping completely non-resonantly, but by utilizing the vibron in the structure, what we could do, we could actually observe that we can lower the threshold dramatically. So we could lower the threshold by a factor of 10. a bit more than 10, 1 order of magnitude lower threshold, by allowing for polaritons to jump to the ground state through the emission of one vibron. Okay, so you accelerate very much the relaxation of energy. Now, once you do that, to do that, first of all, you need to pump resonantly a hot exciton reservoir, which is exactly one vibron above the ground polariton state. By doing this, we create here a coherent state, a polariton Bose-Einstein condensation, which was at lower threshold. Polaritons didn't have to come across the dispersion, just through the emission of a vibron were coming here. And now having this very low threshold polariton condensate, we thought of actually trying to see if we can stimulate, if we can seed the condensation. So if we pump optically hot excitons just below the condensation threshold, and then we bring a control beam, which is resonant to the ground state. This is similar to the concept of a laser. We put one polariton at the ground polariton state, so we create occupancy of one, and then all polaritons in the structure, they come and they coalesce at the ground state. So we create polariton amplification. It's not condensation anymore because there is no thermalization, but it is polariton amplification here. So if I look at the dispersion of the system, without the seed, I get a very nice distribution of energies. And if I look at the spectra here, this is a study that we did previous to this one, we see that we have very nice thermalization of the carriers, etc. When I seed the relaxation at the ground polariton state and I have amplification, I see that I amplify exactly the range of wave vectors that I have injected inside the system and at the energy where I am injecting them. And now if I compare the threshold, I see that I have a much lower threshold in the case of the control in the presence of the control beam. I can have a 50 times rise in the relaxation efficiency. I can really get amplification or condensation, if you want colloquially, on demand. So by doing that, we could really put together all the characteristics of a transistor, so we could demonstrate that we can amplify the control beam, and we can report actually amplifications that reach 10 decibel per micrometer net gain. This is some of the highest nonlinearities ever reported, and the fact here is that we are using the process of polariton stimulation through the vibron emission. Then we could show here that the timing that it takes to switch the system on and off, it is a sub-picosecond, yes, with a switching energy of 1 picojoule at that time. Then we could show that we have an extinction ratio between the on and the off state of up to 17 decibel, which is actually a very good number for optical differentiation of an off and on and off signal. And then we could put 3 of these polariton condensates, controlled polariton condensates together and really connect them in a way where we devise the AND and the OR logic gates. Putting 3 transistors together, you can make a logic gate. So these results were published back in 2019. It was our first success at Scotland with IBM. Those were the days. And then we looked into if we can actually switch on and off the transistor with one photon. Just send with one polariton, just inject one polariton inside the system, and if this one polariton, one photon switch would do the job. So in 2021, we managed actually to tune the structures and all the optical setup, which Professor Kilin has seen actually at Scotland. It is a mammoth setup. But really what we could show is that by tuning in the structure with vibron resonance in an optimal way, we could create, this is the emission of the condensate, this is dispersion in plane momentum and energy. And by putting a control beam, you can see that we can amplify a lot. As we reduce the energy of the control beam, we can still at 1 attojoule differentiate clearly the emission pattern from that of the spontaneous condensation. Now, if you do this systematically and you just measure average number of photons, you see that here we have a contrast of the spontaneous condensation versus the seeded amplification that goes from something like 1000 with 1000 average photons down to 2025 when we are approaching 1 photon in average per source. However, when you do this kind of integrated measurements where you average over several pulses, you are limited by Poissonian statistics because when you want to see how many photons you have in each pulse, well, average measurements will not give you the exact distribution. Even at the state where you have one, you have an equal number of 1 and 0. So at that point, we devised a single shot characterization setup. So for every pulse of light that we send, and these are femtosecond pulses, for every pulse of light that we send on the structure, we can do the full spectroscopy. We can measure the dispersion, we can measure the coherence, and we can also accurately characterize the intensity of the beam before it reaches the sample. And here you can see with the black dots the emission from the spontaneously formed condensate, and with the red dots you can see the emission when we seed with some particular energy, with a certain number of photons. And each dot that you see is a realization of this condensation or amplification process. So for every pulse of light, we do the full characterization, hundreds of thousands of those, but as we reduce the energy or the number of photons on the control beam, we see that when we are approaching now 1, we still have a 10% contrast between the spontaneous condensation and the amplification. So really just down to the 1 photon, we would discriminate in 10%, not 17 dB, but with 10%, we would discriminate the on from the off state. So when we put together this optical switch, if you like, we were very happy at the time. However, one of the reviewers wrote the news and views in age photonics on the transistor, and he said, all good with AND and OR gates, but if you don't have the inverted gate, the NOT gate, you cannot have full logic. You can play, but full logic, you need the inverter. You need to be able to switch a very strong optical beam with a very weak optical beam, which is resonant with. So that was back in 2019, and that actually was a challenge, because if you want to really go in the direction of optical computing, AND and OR gates don't do. You need full logic. Full logic means the NOT gate. Okay, so then what we did, we tuned our system in order to have the non-ground state where the control beam comes not at k equal to 0, but the control beam to come at a small angle and slightly higher energy. And we tuned the pumping beam so that we can create an exciton reservoir where the one vibron is not exactly above the ground state, but from a non-ground state condensate. And now the experiment becomes actually quite trivial. If you do that, and of course, the fact that you are not dealing just with a parabola, but polaritons can move in the plane in 2 directions, you deal with a paraboloid. Yeah, if I rotate the parabola that I was showing you before as the lower polariton dispersion, I can put more of one of these control or seed beams to create seed amplification at the non-ground state. So really the proof of concept is to show that I can amplify a beam not at the ground state of the polariton dispersion. And this is what we set out to do. We studied numerically as a function of the thermalization in the system and the in-plane momentum of the photon that we inject, where we can really compete with condensation and get amplification of a non-ground state. And it is actually quite stringent conditions. This is the blue area of this phase map. We are operating here at the green dot. And indeed, what we could see is that we can amplify the seed from a non-ground state and get the line width narrowing, the energy seed, and the nonlinear emission that we saw from polariton condensation or polariton amplification from the ground state. So if I put this together, it tells you the following. In the absence of the control beam, I have the output of the condensate from k equal to 0, from normal incidence. Now, when I put the seed at an in-plane wave vector, I switch off the output of the condensate. So that's the NOT gate. So let's look now at the emission spectrum. If I have a seed fluence for the control beam, which is very small, you look here at the emission from the condensate. And as I increase the seed fluence of the control beam that comes at the non-ground state, the emission of the condensate is switching off. And clearly here it's switching off over orders of magnitude. So a small control beam can switch off the emission from the condensate by more than an order of magnitude. Well, that is the NOT gate. The NOT gate, the inverted gate, instrument for full logic, Now let's use the fact that we have a polariton dispersion. So let's comprise now the NOR gate, the first universal gate. So without any input, and my inputs will be coming at two in plane, opposite in plane wave vectors, I get the emission from the polariton condensate. If I put the seed beam here, I switch off the emission from the k equal to 0 state. If I put the beam there, the control beam there, again I switch off. If I have both of them there, both of them get amplified, and I still switch off the condensate. If I compile these four elements, it is the NOR gate. And now what we can do for the NOR gate, you need few transistors in electronic transistors. We can go yet one step further. We can use the fact that we don't just have a parabola, but we have a paraboloid. So now we can engineer our optical beam in a reciprocal space and bring several seeds at, so practically we control the angle of the control beam, and we can have several of them. This is now reciprocal space, kx, ky, so the in-plane momentum of polaritons in the plane of the cavity, and here is where I will be bringing not just two in opposite wave vectors, but several of them, 8 here of control beams. So in one gate, in one transistor, what we are showing here is that we can have 8 inputs. So we can create an 8 input NOR gate on a single transistor. That gives you a compression of the scalability of 64 at least. Actually, if you look at it from a logic gate electronic transistor perspective. Of course, if you have gates, as we have shown with the AND and OR gate, you need to be able to cascade them. Cascadability is very important for any logic operation. So we set out to cascade those. So practically couple two of these NOT gates so that when one is off, so practically you have the first one is off, so you can operate the next gate. And we are doing this, I show you here in reciprocal space. When we pump one gate, I get the condensation. When I pump the second gate, I get condensation. And now, when I pump both of them and I take the light from one of these gates to the other gate, practically I can use the emission of the first gate to switch off the second gate. So here the condensate from the second gate, which is here in the circle, is switched off, and I amplify a non-in-plane wave vector. So here we have some cascadability with all the characteristics and an extinction ratio of 13 dB of two inverter gates. And practically then, you need to think, how are you going to scale up? How are we going to put thousands of these transistors now? Because few, as I have shown, is not enough for logic. And that is where actually we engineered an alternative design of cavities, which looks like dominoes on a plane. Forget about the planar cavity that I was talking about before. Imagine that you have a silicon wafer, and on this silicon wafer, you are engineering dominoes from silica. Now, the contrast of refractive index here is forming an in-plane cavity on the wafer. And practically what I can do now, I can create polariton condensates at any junction I want, and I can also couple them through the wave guiding effect of these domino lines. So this kind of work attracts a lot of attention. Unfortunately, our collaboration with IBM was terminated, but we are carrying on with structures that now we can actually devise with each Scotech. So this was the work that we were doing with a group of Ryan and Mark at IBM and the people at Scottex. And the work continues now with perovskite microcavities from ITMO. If any of you are interested in 2D materials or perovskites or organic semiconductors, we would be very interested to discuss with you. Now, this was the first part of the talk where we were dealing with optical computing, yes, digital logic, transistors in an on and off state. On the next part of the talk, I will be talking about analog simulators or optimizers, where practically you are using a system that minimizes Hamiltonian, and it allows you to solve problems that scale exponentially as you increase the number of variables. If you have any questions at this stage on the first part, I'm very happy to take them before we go to the analog computing, which has different rationale. No, okay, so everything is very, very clear. So here we will be talking now about not digital computing, but analog computing. I will give you a brief introduction in the field, but what I will show you is that we can use polariton condensates to create a polariton simulator that minimizes the XY model, the XYZ model, but also the Ising model. Okay, so it is a system where if you play either with the polarization or with quantum vortices in these condensates, you can go between three very different spin models, and different problems have been mapped on different spin models. Okay, so what is a simulator? The concept of a simulator is that it is a problem-specific solver. So what you see here is the Antikythera mechanism. The Antikythera mechanism was a device that we found 150 years ago off Peloponnese in Greece. And when they did 3D tomography of this X-ray tomography, they figured out that it was actually much more complex than what they saw. And it was nothing else but an orrery. Now, what is an orrery? This is a funny English word. An orrery is a mechanical device that actually predicts the position of the planets in our solar system. So the Greeks had devised a mechanism where, with some initial input, they could use it for navigation by really looking at where the stars are. Okay? And when they did that, why I call this a simulator, they had no knowledge of Kepler's or Newton's laws. So what they had done, they had created a mechanical contraption which was mimicking the Hamiltonian of our solar system. That is a simulator. I don't have the analytic solution, but I can mimic the Hamiltonian of the system. Okay, so nowadays, simulators are a bit more complex. They are really allowing us to address problems where, as you increase the number of variables, the worst case complexity goes with some exponentials here, which exceed anything that we would be able to solve, even if we have infinite computational power from our supercomputers. But how do we do now simulation? Really, under every simulator, no matter what is the platform, lies a spin model. And the way that we do simulation here is the following. We map the degrees of freedom to the spins of our spin model. Then we map the cost function to the Hamiltonian of the spin. Then we have to be able to control the couplings between the spins. Yes? So in the simplest Ising chain that I show you here, I should be able to control nearest neighbor coupling. Yes? And this is the input to the Hamiltonian. Then I let the system relax and I look for the ground state of this spin Hamiltonian. Okay. So in these simulators or quantum simulators, and I won't go into the nomenclature, there are many different platforms, arrays of quantum dots, NV centers as well, polar molecules, optical lattices, nuclear spins, superconducting circuits, others. And actually in 2017, we introduced the concept of polariton Bose-Einstein condensates as a platform for simulation. And the advantage that this platform has is that it has direct access to the properties, as I showed you, through photoluminescence. So when I have a polariton condensate, I don't need to destroy it in order to measure its properties. I just look at the light that leaks out of the cavity and I measure the spin or degree from polarization, in plane momentum, from the angle with which the light comes out, the energy obviously, and I can do interferometry and measure the phase as well. So I can measure everything without touching the light. So then, once I have measured everything, well, potentially I can also electrically pump it, which really creates a device, yes? Okay, so what is now the concept of getting the ground state of the spin Hamiltonian? Here I have plotted with a red line the simplest profile of 1D spin Hamiltonian. And now the simulator, what it does, it actually looks for the ground state. You can look for the ground state in different ways. You can throw some particles onto this landscape, energy landscape, and look for the ground state through thermal annealing. So you heat it up a little bit and you wait until all particles go to the ground state. Well, if you do that, you hope that the ground state is so deep that actually you will not have re-excitations. That's why thermal annealing usually does not work. Then you can go to quantum tunneling, where most of the platforms are used, most of the other platforms are utilizing. So the quantum tunneling relies on the fact that I can cool my system down, I can get rid of thermal re-excitations from the ground state, and if I happen to be having particles on local minima, I rely on quantum tunneling to go through the barrier and into the ground state. And like this, I can accumulate all of my particles at the ground state of the Hamiltonian, and that is the solution of the problem. The minimum maps actually the minimum, or depending on how you define the problem, the maximum of the cost function. Now there is a third way where you can reach the ground state, and that is through bosonic stimulation. So the way that this works is the following. You have a system that when it hits threshold, and that can be, for example, a system of coupled OPOs, of coupled lasers. Yes, this was demonstrated in 2014, where they had 4 coupled OPOs, and they showed that when the 4 OPOs lock in phase and hit threshold, they find the ground state. And I'll tell you about the work we did in 2017. So really, bosonic stimulation tells you that when I hit threshold, for Bose Einstein condensation or for lasing, the system hits threshold at the ground state. And if you want to visualize this, imagine of Sahara Desert. And now someone sends you to find the deepest point of the Sahara Desert. Well, that is a very painful task. If you go through thermal annealing or quantum tunneling, it can take forever. Thermal annealing because you can have the excitations, quantum tunneling because the first excited state, the next local minima, could be very far, that it will take the time of the universe to tunnel through. And now, how would bosonic stimulation work? Now, imagine that you fly on top of Sahara Desert, and now someone is filling it, let's say, with oil underneath. The first glimmer of light that you will get corresponds to the deepest pit of the Sahara Desert. So when the light surfaces, it will first surface at the ground state of this complex potential landscape. And that is really how bosonic stimulation works for finding the ground state of the spin model Hamiltonian. So I increase the number of polaritons. When I hit threshold for condensation, my system practically condenses at the ground state of the XY model. And this is what we demonstrated in 2017. Just a few words about the spin models. All of you are familiar with the Ising model, where I arrange my spins as discrete up or down spins in a checkerboard information, and the input to the Hamiltonian is this Jij, the coupling between the spins. There is another model, the so-called XY model, a continuous variable model, where practically again each circle here is a spin, and the dial is a continuous variable spin. So this is spin down, spin up, but the spin can have any angle in the plane. That's the XY model. And it is very similar to the Hamiltonian, but now Jij, and the angle difference between the two spins is the components that go into the XY Hamiltonian. So what we control, if you like, is the Jij, and what we measure is the relative angles of the spins. And then practically you want a system that will find the ground state of this spin model. So that's where we use our polariton condensates. And now I will tell you a few words about how polariton condensates talk to each other in order to minimize the spin Hamiltonian. So when I create with a continuous wave pump, I pump non-resonantly an electron hole plasma or an external reservoir, and I get with a gray dust line here the density of polaritons. And if I go above threshold, I get a polariton condensate. If I look at real space, it looks like a laser. I have a very bright spot. If I do some careful analysis of the decay, I see that polaritons propagate in the plane of the cavity in all directions, and I have an exponential decay. It's actually the Hengel function. If I look at reciprocal space, what I see is that polaritons, in this particular configuration, where I have a very tight spot, they don't condense at k equal to 0. They condense at a very well-defined ring. So polaritons, they actually fly in the plane of the cavity once they condense. And the reason that this is happening, here you can see it in the dispersion. So now we are in an inorganic cavity, and you can see that the exciton-exciton interaction, which is present here, instead of giving a condensate down here, it gives me a condensate with a very well-defined in-plane wave vector. And that comes from the repulsive interaction between the polaritons and the exciton reservoir. So imagine now that this condensate expands in the plane, and I will go and actually measure the phase of one condensate. These are experimental measurements. You can see that the phase is a cartwheeling phase, yes? So as they propagate in the plane, the phase cartwheels between 0 and 2 pi. And now what will happen if I put two of these polaritons? So this is a real space photoluminescence image. One condensate, another condensate. If I increase the separation distance, I see fringes forming in between. And now, if we have some students here, I would like you to guess what is the phase configuration that corresponds in these two condensates. I have a dark notch in between. So what would be the relative phase between these condensates? If one condensate was 0, the other one would be pi. Yeah, they would be out of phase so that I get a dark notch. In this configuration, I have a bright notch. They would be in phase, the condensates. Let's do the following. In order not to play with 0, pi, pi over 2, let's map the phase of the condensate to spins, okay? If I map the phase of the condensate to spins, here I have antiferromagnetic coupling, here I have ferromagnetic coupling, and so on. I map the phases of the condensates to classical spins, and now I can, by reading the interference pattern, or by doing actual interferometry, I can measure the phases. And the whole point is, how do I control the coupling between the condensates? Because now where I'm heading to is the XY model. Imagine that the phase is not just 0 and pi, we can have other phases. The phase can be anything between 0 and 2 pi, and I can control the coupling. I can put together the XY model. So this is what we did. Back in 2017, we created different lattices, experiment and theory, of polariton condensates, and we found out that actually, when they condense, what they do, they minimize the phases, will arrange in a way that minimizes the XY Hamiltonian. So at threshold, they will not have just 0 or pi phase. If I create a graph, an irregular arrangement of the condensates, the phase configuration will minimize the XY Hamiltonian. So we were very happy with that, because then we could take this and apply it to real-world problems. But before I go there, let me tell you how we create these lattices. We use optical spatial light modulation techniques. So we bring the excitation laser onto the microcavity, passing it through a spatial light modulator in Fourier space, which allows us to control the shape of the pump beam. So we start with a Gaussian beam, and now we can generate any array of spots, which we can modulate and make them dance around the video array. And of course, if I come now and I look at the emission of the condensate, not at the laser intensity, but the emission that comes at the energy of the condensate, I see fringes. These condensates are coupled together. They find different phase arrangements, which, as we said, minimize the XY. And then, because I like very much to be in control, being Greek, we really developed very high purity feedback techniques and nonlinear techniques. And these are not numerical data. These are polariton condensates, real data, spatial arrangements in different lattice configurations. And you can see the purity of these polariton condensates in our labs at Scotland. So through this, we can now control the couplings, and we can play, for example, with generating synthetic band structure engineering and study non-Hermitian topological phases in arrays where we play, for example, with coupling between condensates, alternating between A, B, A, B, putting an effect of B, P, A, B. So you can really play with this system as you like. We can create topological charges by creating now polygons where the phase, as it goes around, and you close the loop, so you go from 0 to 2 pi, so you can have a quantum vortex as you go around the polygon of condensates. But as we showed here, we can create giant vortices. We can create vortices of multiplicity 3, higher order topological states. in this system, we can measure the reciprocal space, extract the phases, etc. Then we can arrange them in ways where we create Lie lattices with blunt band condensation. So we can really have dispersion of polariton propagation inside the system. So we can study very interesting physical phenomena, mapping it in our polariton lattices. But at the same time, we wanted to see if we can actually solve problems. Problems which are not interesting for physicists, but they are interesting for engineers. So what we did, we found a way to map, to discretize the XY model on a ternary basis of spins and really map the phases that we measure onto the max 3-cut problem. So which is the set when you have a loosely connected network, which are the 3 sets that cut more of the edges between the nodes. And we did this, and we found that actually we can apply it on image segmentation. So for example, we can use a 3-color image, and by putting this into our system, we can actually see that the phases recognize different parts of the object. Yes, so you take a real problem, you map it on the ternary phase space of the polariton lattice, and the system, when it condenses, finds the phases arranged in a way that distinguish between different objects. Now you will tell me my computer can do that. Yes, but our system, because it is ultra fast, as I showed before, finds these phase configurations in less than 100 picoseconds. Your computer in 100 picoseconds has 1 flop. Yes, this lattice has identified the different segments of the image in less than 100 picoseconds if you time. Of course, there is the problem of measuring, of recording it and looking at it, but the solution is there. Then we can apply it to the max 3-cut problem. So this is the max 3-cut on constraint via minimization circuit design that comes to your phones and your computers. There are actually the circuit boards that we have. In order to reduce the cost, you want to minimize the number of bridges, the number of crossings that you have between wires. And of course, we don't have just one plaquette. We have stacked plaquettes, and you want to minimize the number of bridges between the plaquettes. And we did the same thing here. We mapped the system onto our lattice of polariton condensates, and we found out that actually our system can give us the optimum solution to the problem. Okay, then we were looking into how can we build up. And can we build up by going from the XY to the XYZ? So what is the XYZ? I add 1 more degree of freedom on the spin of the system. How can I do that for something which is mapped on the phase? The phase goes between 0 and 2 pi. Well, I cannot add the 3rd degree of freedom to the phase. So what we have done, we have now utilized the fact that we are dealing with a spin on condensate in a semiconductor. And when I apply an external magnetic field, I split the spin up and spin down components of the polariton condensate, which are coupled through Josephson coupling, and that gives me the 3rd degree of freedom. So we worked with polariton condensates coupled in magnetic fields, and we could see that here, if you look at the parity, by controlling the magnetic field, we can control the coupling. And we scaled this up to lattices and showed that actually the phase arrangement is minimizing now the XYZ. Of course, the XY and the XYZ models are very nice, and I was very happy that we would do it, but there are very few theoreticians that can work with us and map problems on those, because traditionally complexity theorists have been working with the Ising model. Very few problems are mapped on these XY, XYZ models. We had to map some ourselves. It is a very painful process. If we could work with the Ising model, most of problems have been mapped on those. So how can we now go from something which is either XYZ or XY, the phase, the relative phase between condensates, to something which is a discrete spin, either 0 or pi? Well, let's look at another property of the polariton condensate, which, as I said, there was some indications that it is a superfluid. And one of the most beautiful experiments of superfluids, just a few words about quantum vortices in superfluids and superconductors. So on Shangari 49, with Abrikosov in 57, they stipulated that in superfluids you can form quantum vortices that carry quantized orbital angular momentum, that is a superfluid, allowing the superfluid to rotate. In a superconductor, the vortex carries quantized magnetic flux. Many people here will be working with superconductors, but also in superfluids, you have quantized orbital angular momentum. And actually, quantized vortices in polariton condensates were demonstrated back in 2008, and even half quantum vortices, where you take into account the spinor component, were demonstrated in 2009 by Pavlos Lagoudakis. That's not synonymity, it's my younger brother. Right, so the spontaneous formation and a defect of the structure of quantum vortices, they were observed. However, in a superfluid, you get quantum vortices forming when you make the rotating bucket experiment. That's a beautiful experiment where if I have a fluid, a classical fluid, and I put it in a bucket and I spin the bucket around, the classical fluid goes against the walls. Do the same thing with the superfluid, and what you get is flat surface and vortices forming inside the superfluid. The first experiments back in 1979, where they showed that as you increase the speed of rotation, you get formation of quantum vortices in helium superfluid. And here you can see the frequencies. These are several seconds, 0.3 hertz. They repeated in 2000, just before they got the Nobel Prize, where they did it with atomic Bose Einstein condensates. They rotated with optical beams at 150 hertz, Bose Einstein condensates of atoms, and they showed vortices appearing inside. Now, if you want to do this with polaritons, a system that has a lifetime of 10 picoseconds, and the interactions are really on the picosecond time scale, the rotation cannot be mechanical and cannot be done by steering an optical beam with acoustic modulators as they did here. You need to find a different way. You want to be rotating with gigahertz precession frequencies. So we devised an experiment where practically we used some of the knowledge that we acquired back in 2013, just before I started thinking about moving to Scotland, where we could create the condensate by pumping the structure with a toroidal beam, with a circle. And when we pumped hot carriers with a circle, we found out that the condensate forms in the center of the circle. So if you look at here, this is the energy of the emission, and color is the density of the emission. Most of the where you pump, due to the repulsive interaction, you have high energy, and in the center of this cross-section, you get most of the polaritons. And when you look at that, practically you get a polariton condensate that forms in the center of that ring. It is like a hot cup of tea. The hot carriers, they fly out. Now, how can you take this trap? Because I created my bucket here. Yeah, I have my bucket and the condensate there, and rotate it in a way that polaritons will see. So then we devised the rotating bucket experiment in the following way. We use Laguerre-Gaussian beams, so optical beams that they carry angular momentum. We combine two of them, and we combine them in a way where we can control the relative frequency, the frequency of the lasers, so two different lasers, but they are locked with each other, even at different frequencies. That is very difficult. And you can play with the angular momentum of the two beams. And when you do that, what you get, when you combine two Laguerre-Gaussian beams of slightly different frequency, you get a pumping profile that looks exactly like this. It is a bell shape that rotates at the frequency of the frequency difference of the two lasers. Now, if you look at that, if I pump my exciton reservoir here, and I expect that my condensate forms in the center, this is not a symmetric object. So practically polaritons can fly out from the gaps. So now I can exert some torque to my polariton condensate. So when we do that, we use two spatial modulators, two lasers, we mix them, we pump now the structure, we pump the exciton reservoir like that. And when I look now at the polariton condensate emission, the ring, the dotted ring is where we pump. The color that you see here is the intensity of the light that comes from the condensate. It forms a very nice vortex, really a very nice clear circle of the polariton condensate, which is in the center of this bucket where I pump the carriers non-resonantly. And if I look at the energy dispersion here, I have a clear single mode state. But of course, that could be anything. I need to measure the phase. If I want to say that I have a quantum vortex, I need to measure the phase. So we do interferometry of the emission, and when we extract the phase, well, we see here clearly that the phase goes around between 0 and 2 pi. So I have a flow of particles that go around this ring, and when they close the loop, the phase goes from 0 to 2 pi. So I have a quantum vortex, which is now created when I rotate the bucket of the condensate. And I can control the winding by controlling the rotation, either by changing the sign of the Laguerre-Gaussians or by changing the frequency of the Laguerre-Gaussians. And therefore, now I can play also with the frequency. If I rotate very slowly, 0 frequency, well, nothing happens. There is no vortex. Polaritons just escape within their lifetime from the gaps. If I rotate too slowly for the dynamics of polaritons and that of the external reservoir, nothing happens. Once I go to the 5 around between 2 and 5 gigahertz, I see that I get vortices with 100% repeatability. If I go even faster, what happens is that the exciton reservoir that I inject, it has some lifetime of the order of a few hundred picoseconds. And now what I do, I smear this dumbbell that I was rotating so that practically for polaritons becomes a perfect circle. And then again, in the perfect circle, there is no torque and there is no polariton quantum vortices forming. So this work was published actually just a year ago with Ivan Knusov and Sergei Alatin and theory from Southampton, still from Southampton. Then we played with the bucket size dependence. What if we made our bucket bigger so that we can fit more vortices? And indeed, we see that we can form 2 quantum vortices inside the system. And then we try to see if we can actually do experiments where we use the polarization of the condensate, the spin of the condensate in this kind of rotating bucket experiment. But before I go there, I want to tell you first about the Ising model. So, because probably I will not have time about the NMR data. So, in the next 10 minutes, I will tell you how we use now this quantum vortex as an Ising spin. So, I showed you before that I can create a quantum vortex of polariton condensates, which winds either clockwise or anti-clockwise. Well, let's map the winding of the quantum vortex to a spin. Clockwise is spin up, anti-clockwise is spin down. If I can create this vortex spontaneously, the winding of the vortex can be my Ising spin. So now, instead of creating the quantum vortex as I showed you before by rotating the bucket, I am pumping 6 spots in a geometry which allows the condensate to be formed in the center of the pumping spots. So that is like a loose bucket. Yeah, a loose bucket has losses which practically drive a condensate to be formed here in the shape of a ring. Is that a quantum vortex? Well, if I do interferometry, I find that actually 37% of the times it goes anti-clockwise, 45% of the times it goes clockwise, and 18% of the times it forms a dipole state. I can do single shot realization. I can really initiate my system measuring. And practically I see that, well, for first experiments, almost stochastically, it goes 50-50. Allow me to say that. So, spontaneous symmetry breaking, if it will be clockwise or anti-clockwise. And I will map now the winding number to the spin. So, spin up, spin down. Let's put 2 of them together. When I put 2 of them together, what I see is the following. 7% of the times, I get some configuration with the dipole. I will discard those. And then 53 and 40% of the time, I get anti-clockwise rotating vortices. They don't follow the statistics of the one. They like to go in opposite flows. So practically where they meet, they have opposite flows so that they reduce the friction. So 2 quantum vortices which are coupled, they like to go in an anti-ferro configuration, spin up, spin down. Okay, let's create a lattice because the lattice really gives you the simulator. If I go to a lattice, I need to fix the lattice dimension such that I get a lattice of vortices. And now I have a lattice of vortices, and the coupling between the vortices will give me the input to the Hamiltonian. The winding number, it will tell me if it is spin up or spin down. That's the Ising Hamiltonian. Okay, now, do I have vortices? Well, if I look at reciprocal space, that I see most of the emission is in a ring. So I have non-freestanding polaritons. Yeah, all polaritons rotate around in the reciprocal space. If I measure the phases, I see that stochastically from realization to realization, I see different spin configurations. And if I now go to the next step, this is just what you observe when you inject this lattice of vortices. But what I said in the beginning of this second part of the talk is that the most important thing is to be able to control the coupling between the spins. So how will I control the coupling between two vortices? Well, here we utilize again the repulsive polariton interaction in the following configuration. Let's simplify the problem. Two pumping spots will form two condensates, and then I will put an exciton reservoir, which is sub-threshold, no condensation, just a repulsive potential. And when I look now, the pumping profile, the sub-threshold exciton reservoir acts as a barrier. These are the two condensates in real space, reciprocal space a ring, fringes because they are coupled. And when I do homodyne interferometry and I measure the relative phase, by scaling the height of the barrier, I can control the coupling of the two condensates from being in phase or out of phase in a continuous way. So this potential barrier impedes the flow between the condensates so that it allows me to control the Jij. Now let's do the same thing with the vortices. We also did it for lattices, and we could play between different magnetic phases in frustration for condensates. Let's go to the vortices. If I have two of these rings, the condensates, the quantum vortices occurring between, I will create a barrier, which I will put exactly here. And with the amplitude of the barrier, which is not just one spot, it's a bit more complicated now, I will be looking if I first of all have vortices. It looks like I do. If without barrier, two vortices, and with barriers, again, two vortices. Now I need to see if with the barrier, I can switch the coupling. I know that these two guys, without the barrier, they like to go antiferromagnetically coupled, anti-clockwise rotating vortices. And with the barrier, they go to clockwise. Yeah, both of them rotate in the same way. What does that mean? That means that I can now control the coupling between these two vortices. And when I put all this together, and I'm going to do some statistics, and I distribute my spins between antiferromagnetic and ferromagnetic spins, or free spins, if a spin, so a vortex, has an equal distribution of spin up and spin down neighbors, it's called the free spin, and I take down the average number of spins as a function of the Ising energy, I find actually that my experiment finds the lower 6% of the Ising spin configurations from the ground state. So these are not published results, these results which are in process. So we have now the Ising model, the Ising spin simulator, which finds, it brings us 6% near the ground state. Well, that is good enough for some problems. Okay, so with that, again, now Sergei Alyatkin was the champion of this work with co-workers from all over the place. And before I move on, I will summarize by giving you a snapshot of what we can do with the spin-off degree of freedom of these polariton condensates. So, of course, if you have a spin-up or a spin-down exciton reservoir, it will give you a spin-up or a spin-down polariton condensate. All right. So by measuring the polarization, now I can measure the spinor of the condensate. But if I have a condensate where there is no splitting between spin up and spin down, I can get a linearly polarized condensate. Okay? So if I create an elliptical trap, not a spherical trap, so I pump with an ellipse, I see actually that I pin the polarization, the linear polarization of the condensate on the short axis of the ellipse. So that was some initial work that we did in 2021. We could create a condensate where by rotating the ellipse very slowly, yeah, not with combined beams, just with conventional optics, we could really rotate the linear polarization of the condensate. But now we can rotate it with gigahertz. So let's see what happens. I put now my composite beams, and I have a pseudo-spin, if you like, of 1/2, which is on the XY plane of the Poincaré or the block sphere, as you like. And now I can rotate this with gigahertz. So let me do it. And what we see is the following. If I rotate slowly, microseconds, 0.2 microsecond rotation, yeah, I see that the 3 degrees of freedom here, so horizontal, vertical, diagonal, it rotates on the XY plane, the polarization of the Poincaré sphere. So I have a linear polarization that rotates slowly and it follows the rotation of this elliptical trap. Okay, so it follows the rotation. Let's go now and do it fast, really fast. How fast? So fast that actually, if I look at it, I rotate it as fast as the intrinsic degrees of freedom of the splitting, of the spin splitting in the structure. And what we see here is the following. When I control the intrinsic spin splitting by injecting not an equal portion of spin up and spin down electrons, but an asymmetry there, which creates an energy splitting between the spin up and spin down polariton, and I rotate at this frequency, I hit resonance, and practically I see a spin precession that lives as long as our experiment. We have gone to microseconds. So I can now go and have optically driven spin precession inside this polariton trap, and I can go and do the classic experiment of measuring the spin coherence, and we see that we reach spin coherence of 320 picoseconds for a system that interacts within a couple of picoseconds. So I have room for a lot of operations there. And then with that, I will close. That was, I know, a bit too much. So I will close by saying I hope I communicated, first of all, the most important thing, what is a polariton? An admixture of an exciton and a photon in a cavity, bridging two fields, which allows us, and the goal of our lab is to look into optical computing, single photon switches, universal gates, and analog computing, XY, XYZ, and Ising simulators and optimizers. And with that, I would like to thank all the people of the group that contributed to this work, and you for your patience and your attention. Thank you.
Thank you very much. Very nice presentation. So the lecture is open for discussions, for questions. So please ask Pavlos. Okay. For me, it's fantastic to working with Bose condensate as a unit for any kind of simulation and controllable simulation. The question is about you showed the coherence of this structure, how long it can be survived for operations and
Yes, so there are different coherences here. So we have the coherence of the condensate, so the phase of the macroscopic wave function that defines the condensate. And in the case of the traps, we can reach few nanoseconds. Then we have the spin decoherence time, which is different, and that is 320 picoseconds. We did the first, this is the very first measurement in all polarity condensates. But of course, one needs to consider how strong is the interaction between polaritons. Because if you remember from the work on the optical transistors or the earlier work on the condensates, we saw that within a picosecond, we can flip states. So within few picoseconds, I have strong enough interactions to switch things around. That be the spinor of the condensate, the coupling between condensates, and then I have, when I deal with the polarization, the spinor, I have 320 picoseconds to do some operations. In the case where I don't care about the spin, so I can create a system where all the spins are spin up, so practically spinless, yes. Then I have a coherence of 4 nanoseconds, again, with few picosecond interactions, yeah. So I have thousands of interactions that I can allow in the system. If you compare it with optical lattices, well, they have condensates that live for very long, yes, but the interactions are extremely weak. We need to be comparing the interaction time with the coherence time, the alpha time.
Brilliant science and brilliant scientists. Thank you so much. Thank you. Thank you. Approximately 33 decades ago, there was very extensive activity over the world towards optical computing and photonic switching. By the way, to younger part of our audience, in 1992, we hosted big international congress, which was called Optical Computing and Photonic Switching. In 1992, here in Minsk. Our institute pioneered, by the way, in semiconductor optical bistability.
Yes.
The very first work has been done here in this building. Yes, in 1973, approximately 1973. And we had, till now, we have good vacuum deposition techniques, and we can make cavities and laser mirrors and so on, so forth. And the question is that at that time, this research had been stopped because opponents were very serious opponents. They told there is a very unfavorable overall energy balance because we need to keep on population of optically excited entities. Species anyway, should be atoms, molecules, or excitons or polaritons. We need to pump up the matter and to keep on population continuously or quasi-continuously. And this is drastic for energy balance during computing. Yes. In your case, do you overtake this problem or not? Do you still need to make quasi-continuous pumping of matter inside cavity to keep on polariton population quasi-continuously?
Okay, thank you very much. Very, very good question. So I wasn't even born back then, I have to say. Maybe this is the very first experiment, but I'm aware of some of the work. Again, in the 90s, when the optical computing was revived, it stopped again because of this issue, but also from the issue of the weak nonlinearities that they were observing. So they were requiring very bulk crystals. They could put few together. Now, the energy consumption, when you deal with bulk crystals or with semiconductors, like the work that was done here, semiconductor bistability, you need to be in the quasi-steady state regime. So you pump continuously.
Exactly.
Now, in our case here, the reason also we demonstrate that within a picosecond we can switch on and off is that we can pump with femtosecond pulse. So we send a femtosecond pulse, and that creates one bit. Now, the condensate appears, and then it disappears within few picoseconds. So instead of pumping continuously, we pump with femtosecond pulses, but the clock rate is the rate of the pulses, yes? So we can go to several megahertz, maybe we can drive it to gigahertz. With different materials, with inorganic structure, we could definitely go to tenths of gigahertz. And then there are two energies which are of relevance. One is the switching energy, where we could demonstrate that we can switch on and off with one photon. That you cannot do better. However, there is the bias energy. And the bias energy, it is still actually not favorable if you want to go beyond the 1,000 transistors for the type of materials that we are using. So this was work that we had until a few weeks ago when IBM put out. This was their part of the project, to identify the type of materials where we can lower the threshold for condensation and come close to something where we can work with, a few tens of thousands of these transistors, putting them together. So this remains a challenge. We don't do quasi-steady, we do pulse, but still there is substantial amount of energy for reaching the condensate. For switching on and off, one photon. But the challenge remains. Thank you.
May I have one more question?
Yes, please.
What is the actual Q factor of your cavities? Q factor of your cavities.
Yes.
And maybe one more. Okay. If you allow me.
Especially if you can make this kind of laser cavities here, we should have many more. The Q factor of the cavities is between 500 and 10,000. For the organic microcavities, the microcavities that IBM was making, it was between 500 and 1,000. These are the structures that they were working at room temperature optical switching. the inorganic microcavity, so the gallium arsenide 112 microcavity, there we could reach a Q factor of 10,000. Yes, the longer the Q factor, the longer the lifetime, the lower the inputs that we require for threshold. And so there is an interplay. But if you want a very fast switch, you can lower the Q factor. So we have another paper coming up where we say that if you want to be switching with 500 femtosecond, you cannot have a cavity lifetime which exceeds 200 femtosecond. Why? Because then your state lives there even if you do it something for longer. So you need to reduce the Q factor, increase the threshold, achieve higher speeds. So there is a balance.
Yeah. Thank you. That's all.
More questions? Okay. I have. Okay. Can we compare the possibility to make this simulation of Ising model, which is usual for this simulation for quantum people, D-Wave company and opportunity of your system? Can we compare?
Well, before I came to Scotland, I was full-time in the UK. And at that time, there was a big quantum drive and funding, and we bought the D-Wave device. It's at Edinburgh University, so within the UK. You should look for the papers that came out of that. It is 10 years, one paper.
Yeah.
Why? Because it is not just that it is temperamental, it is the overhead for coupling the qubits, what they call qubits, that is tremendous. So yes, you have the one we got at 1024 qubits, was the best at the time. But the overhead for really making any operation was you required hundreds to couple 3 or 4. So, but it is a simulator, it is not a quantum computer. And if we were to compare it with our device, we have not done benchmarking. I can't say what it will be because we need to have access to it now to benchmark. We can compare with optical lattices. So in optical lattices, where you deal with atomic condensates, that is a more favorable comparison for us and for them because they are the superconducting qubits. So then we have the advantage, which is it is the following: when you deal with an optical lattice of atomic condensates, so you distribute your atomic condensates in a lattice, and then you control the lattice geometry in order to control the couplings between the condensates, then you want to measure the phase, the XY model with atomic lattice. Yes? How do you measure the phase? Well, you remove the trap that creates the lattice, you make the atomic condensates expand. As they expand, they interfere. You measure an interference pattern, which is not interferometry, it's the same as it comes out of photoluminescence, and this is a snapshot of your experiment. Then, if you want to change the parameter, you create another optical lattice, you change. In our case, we can actually create a lattice, real-time measure the coupling, and real-time modulate the coupling as well. So it is a much more flexible platform. And we can go to a few thousands, they can go to a few thousands as well, but we can control the couplings. We just, and that's why I always emphasize JIJ, the input to the Hamiltonian, if you don't show that you can control it individually and not across lines, because what the people with atomic lattices do, they use different lattice constants across different directions. They interfere laser beams. When you interfere laser beams, you get geometries that they have axial symmetry. So you change all the couplings in one direction. You don't change one. Here, what we show is that we can engineer each individual coupling. Thank you.
And the symmetry, all what we see here is hexagonal symmetry like that. You play with another type of symmetry, rhomboids and like that.
Yes, so we play with regular lattices, but in view of our collaborations as well, I can tell you that now we are playing with asymmetric lattices. So we have done Penrose tiling, which is very interesting because it gives you answer localization in the reciprocal space. And we have also, I don't know if you have seen the literature from April 2023, there was the first paper where they managed to make a periodic lattice with a single tile. They called it monotiling. So with Penrose, you have two different tiles, and you can cover the full space with two tiles. Yes. So you have this 11-fold symmetry. They managed to create with a single tile a periodic lattice. And we are studying now this monotile periodic lattices and compare them with the Penrose periodic lattices. And the system is so flexible, which allows us to really go into that, which you cannot get by just interfering laser beams. You cannot get a periodic lattice with interfering laser beams if you want to compare it with that of the space. Okay.
Thank you.